Hello and welcome to this video which covers a very interesting development in telescope mirrors. Now the problem with telescope mirrors are largely but not exclusively twofold as shown. These two problems can lead to considerable production problems and therefore costs. So what methods have been used to try and overcome these problems? One development has been segmented mirrors. Now they are where the mirror is made of a composite of hexagonal mirrors, and these mirrors can be moved individually by control mechanisms. One of the earliest of these mirror types was the Keck mirror, now shown. In the foreground of this image you can see the superstructure, the tubular steelwork which supports the telescope and the telescope mirror. In the background, slightly obscured by some reflection, are the mirrors which make up the individual primary mirror. Now all of these mirrors are individually controllable. So whilst segmented mirrors in theory can be quite large, the main problem with them is individual control of these mirrors, and that again leads to costs. So we're back almost full circle to the problem of normal telescope mirrors. So are there any potential solutions to these problems? Some recent work may well have come up with a solution to the problem of large telescope mirrors produced cheaply, or at least relatively cheaply, and that is what we're going to consider now. Shown here is a container with liquid in it. The parameters are height, y, width, x, and rotation speed, omega. Now these parameters are linked together by the formula shown at the bottom of this slide, and if we plot that formula we get this graph. Now that of course is a graph of a parabola. Now this is not new science. The fact that a spinning liquid produces a parabolic surface has been known about for, well, many years. However, the group's work which I'm about to show you has shown that it can be possible to use this parabolic surface to produce quite large mirrors. So here we have the container, it's spinning, and fairly obviously as you keep up the rotational speed, then the parabolic surface will remain. Now what if you were to introduce a substance into this environment which would sit on the parabolic surface, which would set, and which you could then extract? Well, that is the work which I alluded to earlier, and now shown is the technique which this group used to develop their production method. So here we have the parabolic surface, which is polyethylene glycol. The liquid is polyethylene glycol. The material which will form the parabolic surface, the parabolic mirror is being injected is parylene. The important thing, two important parameters here, is that this process is done in a vacuum, and the liquid used must have low vapor pressure. In other words, we don't want molecules coming up from the parabolic liquid, because that will then get into the vacuum and would deposit on the surface. In other words, it would cause an impurity. So polyethylene glycol is ideal for this. It has very low vapor pressure. Having managed to get a surface on the parabolic surface, the group then were able to remove it and add a reflecting surface to it. So in essence, what they have produced is a parabolic mirror which is very accurate, relatively cheap to produce, at least in terms of when compared to other mirror production techniques. But overall, the most important parameter is it seems to be, from reading their data, that it's extremely accurate. If you want to read further into their work, I've attached the paper that they produced to this video. So anyway, I hope you've enjoyed this short video, and I'll say goodbye. Thank you.